Good morning from Germany. Welcome to my presentation at the GTT user meeting. My talk today would be about looking for future solutions by digging into the past. And I will explain how computational thermochemistry helps us in this aspect on the example of solving some old industrial mysteries. I will start with explaining the past, present, and future situation for phosphorus for steel makers, because this was the subject of investigation during the cooperation between SMS and GTT. So phosphorus is an important and an essential element for life, but for steel workers, it is considered as a problem because it reduces the ductility and toughness of steel. And this is why we have to remove phosphorus from the liquid steel through oxidation reaction, through reacting with the oxygen up to very low value in the range of 70 ppms until 100 ppms. So in the past, back in the 1960s and the 1970s, so the early days of steelmaking, German and also some French steelwork have used local iron ores for steel production. And those local iron ores had a very high phosphorus content, higher than 1%. This is quite extreme compared to what we have today. Still, the requirement on phosphorus are the same as they are today. So the target phosphorus has to be achieved. And this can only be done or was done in the past with a double track strategy. That is a two-step refining with intermediate deslagging in between, which has major economic drawbacks. So the present situation today is that in Germany, we are using now imported iron ores, so mainly imported from Brazil, which have naturally a low phosphorus content in this range, so a big difference. And but still in some other regions, such as Japanese and Indian steelworks, which are some especially Indian steelworks are our customers. We have customers there. They do deal with higher phosphorus content in their iron ores in the range of 0.15 weight percent. So how would the future situation look like? It is expected that an increasing trend for phosphorus in the iron ores and thus in the hot metal will be the situation, will be a reality in the future. This is due to tendency to mine low-grade iron ores instead of high-grade iron ores. And low-grade iron ores have a high phosphorus content compared to the high-grade iron ores with a low phosphorus content. And thus we may have initial values similar to that in India and Japan, in Europe, and even higher. It may be a possibility in the future. So the question is whether the European steelworks would have to adapt their practice to the double slag practice. The green steel transition, the planned green steel transition for European steelworks from carbon-based reduction to a hydrogen-based reduction of iron ores will not improve the situation with respect to phosphorus. So the problem will be there, and it may even sharpen in the future because it may drive the tendency to use low-grade iron ores even further due to compensate because they have a lower price to compensate for the increase in production, in technology, in energy costs. And the double slag practice, in at least in its current version, cannot be implemented in such a case. So it's not a solution, it's not an option. The reason is that this practice is based on the fact that the lowering the temperature results into an increase in high phosphorus removal rates. So the reaction of phosphorus removal is favored by low temperature. So we keep in the first step, we keep the temperature low, and thus we can achieve high dephosphorylation rates. This is possible when we use carbon for reducing, because the hot metal will be carbon saturated and it will have a low melting point, because carbon, as you know, lowers the melting point of iron. So it's possible to get liquid hot metal in this range, and thus it's possible to dephosphorize it at a low temperature. However, if we no longer use carbon for the reduction of iron ores, if we use a hydrogen gas, then we will be getting yeah, more or less a pure Fe, or at least a carbon-free Fe phase. And then the melting temperature would be higher than 1500, let's say 50 degrees. And thus, this strategy, the double stack practice, will not be an option for us. So as you see, we will be facing new situations, or at least expecting that, and thus we need to develop new solutions to remove phosphorus in the future in Europe. So what we have done is that we cooperated with GTT and many other partners in the scope of European project to have to develop the solutions by adapting computational thermochemistry as here to understand the dephosphorylation reaction better. And we have, so GTT have developed a thermodynamic database following the CaO-FeO approach using the thermodynamic compute and software factorization. And here I have listed the different Gibbs energy model for the solution phases and the stoichiometric compounds that we have used. So why did we decide to use the CaO-FeO method? It was because it's a consistent method to extrapolate from known systems, so from system for which we have experimental data, which we know very well, so systems, I would say, from the past, to model the thermochemical behavior of new systems for which we don't have complete sets of data. So systems rather from the present situation or for the future situation. And we can use this approach thus to evaluate and to reflect back on past industrial practices. So we have a large amount of experimental and industrial data for past practices, that these were high phosphorus slags was reduced, high phosphorus iron ores were used in the past. And then we may gain from that valuable information to improve the present and the future practices. So this is the main idea. All right, so I show you the results with respect to some systems today. And so you can see here the oxide system relevant for high phosphorus slags is this ternary system, which is a well-known system. Back in the 1960s, you can find a high number of experiments done on the systems. And here I show you the phase diagram calculated by the database at the reduced BO2 state. That is in equilibrium here with a liquid iron and a temperature of 1600 degrees. So for the sake of visuality, I have for the different phase boundaries here. So for the different regions, I use a different color. So the orange color here represents the liquid slag region. The gray color represents immiscibility gap. So this system is known by immiscibility gap, which is which have quite a lens shape. And the white regions, they are regions which are saturated with one or more solid phases. And you can see here in the diagram the data points that are experimental data from the literature. And it becomes obvious that most of the experimental data describe this line. This is called what we call the lime saturation line. And the reason is that this line was considered to be the target composition of the target region for the slag composition in the industrial process for different reasons. One of them is favoring dephosphorylation with a high lime content, but that's not the only reason. So you can see here this ternary system. We have a good agreement between the data and between this region of the phase diagram. But other than that, this diagram does not give us new information compared to what we know, to what we already have in the literature. It also does not give us, I would say, evaluation on whether this database can extrapolate, or the CaO-FeO, the adopted CaO-FeO approach can extrapolate to new data, because GTT have used already this data for the database, for the development of the database. So let's go to a system which is less known, but we remain within the ternary system. So it is the same ternary components, and it is the same temperature, but now we have increased the oxygen partial pressure. So we have increased the oxidation state of FeO, and we have a much higher Fe2O3 to FeO ratio in the slag. And it's interesting how big the effect that we see here, how tremendous compared to the system we have seen before. So for the sake of comparison, I have included the previous phase boundaries as dashed lines here. And the color, they represent the same thing. So the orange is for the liquid slag, the gray regions, they are the visibility gap, and the white regions are saturated with one or more solid phase. So we see that such a small change have increased the lime saturation of the slag. So the line was here, it's now, yeah, it went in direction of more lime. So the lime saturation increased by about 3 to 8%. And because of this, we see an expansion in the liquid slag region, which means that if for the industrial practice, we would have more flexibility to achieve a fully liquid slag, which is then close to the corner of lime saturation. And this is an important for the industrial process. So at this stage, we can see the importance of using the CaO-FeO-based approaches in general, because we had new information about the behavior of this ternary system, even though it's considered to be well established in the literature. So there were data points, we see here agreement, so experimental data points, but a visualization of this diagram at elevated partial pressure has been missing, or at least I couldn't find a whole representation, so just the lines or general descriptions. For example, that the effect, the miscibility gap shrinks as we see here, but a clear visualization showing the effects of PO2 on the whole ternary system, I did not find something similar in the literature. Okay, so now let me get to the industrial mystery that that I already mentioned in the title at the beginning of the presentation. In the past, in a series of independent plant trials in the high phosphorus system that I introduced in the previous slides, some plant trials reported finding an inexplicably low phosphorus measured in the metal droplets. So about phosphorus droplets had a phosphorus content of 70 ppm, which is very low, it's optimal. Those metallic droplets, they are embedded in the slag samples because dephosphorization occurs as a reaction between metallic droplets, which are ejected from the bath to the slag above, and they react with the slag and come back after residing in the slag, come back to the bath afterwards. This phosphorus was very low, and strangely, the samples had a low FeO content of about 10 weight%. So why was this controversial? The reason is that it contradicts our fundamental understanding of dephosphorization reaction. So dephosphorization occurs following this reaction, and it needs a high oxygen activity in the metal for phosphorus to leave the bath, to leave the metal bath, and to bind, to be dissolved into the slag as this phosphate ion. And to get a high oxygen activity in the metal, we should have a high oxygen FeO activity in the slag. So they are related. It's well established that the oxygen dissolved in the metal depends on the FeO activity in the slag and the temperature of the process as well. So at such FeO contents, and this is the data points here, we were not expecting dephosphorization to happen. and getting such low values even. So the second point is that the laboratory phosphorus equilibrium studies back then have reported that the minimum phosphorus that can be achieved at equilibrium, so very low, excellent dephosphorization conditions, low temperature, lime saturation of the slag, a high FeO content of the slag, the best we can get is 0.02 weight%. So not only was dephosphorization taking place where it shouldn't have, but we were getting values lower than equilibrium. So very strange. All right, so let us reinvestigate this old case, this old industrial mysteries using our new thermodynamic database. So we had a closer look at those studies. Yeah, so let's start with the question, why was phosphorus oxidation taking place at all at such a low FeO? So the industrial studies reported that the samples had silica content in the range of 7 to 10 weight%. So for this, we have then considered the quaternary system, for which, again, a good visualization of the phase diagram has been missing back then. And we can see that when we add 10% of silica to the system, I would say, yeah, a major change occurs almost in all, regions of the system. So we can see that if we compare with the previous diagram here, that the orange region no longer exists, and also this lower part of the miscibility gap disappears completely. So as you see here, and this is now, we are having this purple region for which I wanted to mark. It's an important region containing liquid slag and a so-called C2SC3P solution. This is how we call it, but this is the actually the solution phase decalcium silicate tricalcium phosphate. And so if we look at the previous data point, previously it looked like it's in the fully liquid slag region in the ternary system, but in the quaternary system, it is actually within this region, saturated with solid phase. It is a two-phase region, and the liquid slag composition moves along this green line. So if you see, the liquid slag will always have a composition higher than 50% FeO, independently of where the position of the oxide system or of the slag as a heterogeneous slag. So the heterogeneous slag has 10%, but the liquid slag will always, part of the liquid slag will have a composition higher than 50%. And this is why a high oxygen potential could be established between the metal droplet and the liquid slag part. So the liquid slag part could dissolve phosphorus. Yeah, and this is the answer to the first question. Okay, so how could it be that the phosphorus achieved was less than the phosphorus equilibrium? So this was because the equilibrium studies that were made back then, they were carried out in fully liquid slags because it was believed that the slag is fully liquid or that the ternary system is sufficient to understand the behavior of the slags. And this questions, of course, the transferability of those studies to describe equilibrium in not only quaternary system, but the slag is not fully liquid in the industrial process. It is saturated with C2SC3P. So it's either saturated with only C2SC3P or double saturated with lime and C2SC3P in this industrial region. And our calculations using the thermodynamic database indicated that the solid phase has a great potential for removing phosphorus. So not only the liquid slag can remove phosphorus, but phosphorus can also dissolve in this solid solution. This is already indicated by this part here, the tricalcium phosphate that is dissolved here. And we found out that this phase shifts the phosphorus equilibrium to a much lower value compared to the fully liquid or lime saturated slag, which does not contain the solid solution. So for us, we could find value as low as 40 ppm at similar conditions. So 70 ppm was not a contradiction. Okay, So this is the explanation for the industrial mystery, and we do consider this as an evidence that this solid phase can remove phosphorus in the industrial process. So that's it. To conclude, I would like to say that computational thermochemistry can help us learn from the past in a way that we use old experimental data to develop and optimize the new thermodynamic databases, and thus we can extrapolate from those systems that we know to new systems that we don't know relevant or not yet relevant for future situation, but sometimes also for the present situation. And this reduces the experimental and industrial effort considerably. We have seen today how we can use this approach to reevaluate and reflect back on previous industrial practices to explain some past controversies and thus learn something for the future. So with this, we get to the end of my presentation. Thank you very much for your attention. And I'm looking forward to nice discussions with you on Gather Town. Thank you.